Hello, everyone. My name is Manu Fontaine. I'm the founder and CEO of a cybersecurity startup in the Washington, D.C. area called Hushmesh. And I want to talk to you about agentic identity, global agentic identity, and the ability to establish trust between different agents across the internet, and trust that is not mediated by any domain or administrators or anything in the middle. We're talking about direct cryptographic trust between two agents at internet scale. I'm going to present this innovation in the context of our relationship with NATO DIANA. We fell into the defense use cases. We are a dual-use company. We knew that from the beginning, but we just randomly applied to a challenge that was posted online. We got selected, and then the rest is history. So for those of you who don't know DIANA, NATO DIANA, NATO, you guys know NATO. DIANA is the accelerator for NATO that was created just a few years ago. NATO in general realized that innovation in defense was too slow, and they decided to create that accelerator to just bring industry and startup innovation into the defense ecosystem. It is very much focused on dual-use innovation, so it's not at all just purely defense. It's basically collecting good ideas from industry and bringing it and exposing it inside the defense realm. So our history is longer than I expected. I was hoping that we would go faster, but defense and NATO doesn't move very fast. So we've been working with them since 2004. We basically got selected in the very first inaugural cohort of the accelerator. There was 1,300 applications, 44 startups got selected. That's across all of NATO. We were one of 16 startups in the cybersecurity space. And the challenge was specifically about secure information sharing. And those words you'll see will come back. It's really the idea of being able to exchange information, across, all kinds of systems in all kinds of situations. We basically have been working with NATO and with NATO DIANA in particular for quite a while. And then last year, our technology started bubbling up, and we got included into the first rapid adoption action plan that NATO approved at the NATO summit last June in 2025. In December last year, we did a pilot, a mini pilot with DIANA and with NCIA. NCIA is the NATO Communication and Information Agency, to prove that the technology works. And then just earlier this month, we were quite excited because NATO now approved officially our technology called the Mesh as a standard recommendation. So it's not yet a standard. It's just the first step to expose the technology to the 32 nations of NATO, enable them to just look under the cover and just see if there's something there. Of course, we believe there is. The timing is great because we actually are soft launching our capabilities this month also. So if after this talk, any of you is interested in collaborating, we are looking for partners to play with this. So what is DIANA trying to do? DIANA is trying to create that ecosystem, that innovation ecosystem across dual use, as I said, but across the entire alliance. 32 nations, and they basically are calling startups to show up and respond to those challenges. They organize a network of accelerators across the 32 nations with a network of mentors. They have test centers that enable for all kinds of innovations, right, to go and bang on these new ideas. And then, of course, it's connecting the ministries of defense across the alliance and NATO itself and all its internal bodies. And really when you think about that ecosystem, the idea is to create a front door for innovation. But if DIANA is ever going to be successful, it will end up owning and holding the future of defense, right, within that ecosystem. It's going to become a target. It's going to become, a nation-state center of interest. So they're really interested in having very high assurance of a series of properties here: integrity, provenance, of all information, making sure that we know where things come from, that we have authenticity of all information exchanged. Of course, confidentiality. Sovereignty, as you can imagine, as an alliance of 32 nations, is extremely important. And because these are, startup founders and, normal citizens that participate in this, privacy is a critical concern too. In fact, we're getting trained very early on in the program that, we may become targets ourselves, but just being members of the program. So there's a lot of interesting, dynamics there. NATO as a whole is really talking about zero trust and data-centric security. These are the translation, if you want, of those properties that DIANA is trying to embody. And more specifically, global zero trust is a massive problem for NATO. It's the zero trust across domains, right? It's being able to, across nations, across domains. Domains in defense means, air, sea, land, cyber, space, the different domains, making sure that those systems can communicate across domains, across nations, in all kinds of situations. And so data-centric security, you'll see that we telling NATO we need to recast this and think about entity-centric security. Imagine all kinds of entities, right? People, organizations, physical things, digital assets, and then being able to track and connect those things with global zero trust and full information-centric or entity-centric security. And of course, if we solve that for NATO DIANA, you can see where this can go, right? NATO is a billion citizens, 32 nations, relationships between government, citizen services, all of that requires the same kinds of properties, sovereignty challenges, and then of course all the military use cases, 3.5 million warfighters, trillions of dollars of budget every year, lots of equipment from, again, right, with chains of authorities that go to different governments, different authority structures. All of that needs to be able to interoperate with very high level of assurance. And then, of course, if we can solve that for those problems, our interest as a commercial company is to basically solve that problem across the whole internet, and being able to interconnect people, businesses, nations as entities and sources of authority. Authoritative identity, for instance, is of course always rolls back to governments. Of course, AI, agents, AI, infrastructure, IoT, critical infrastructure, chips and other supply chains. All of those things are the things that we think about when we are trying to design an infrastructure that interconnects all of those things across the entire internet. And then, of course, at this conference, everybody has been talking about AI and AI agents. It is clear that the same properties, and just like you don't want your kids to talk to strangers, you're going to want your agents, to make sure that they don't talk to bad other agents. So we do need a global identity system for agents, and we do need a cryptographic infrastructure to enable those agents to authenticate to each other, to build reputation, to be able to encrypt their own memories, their own credentials, and keep all that to themselves. So we see a massive opportunity in interconnecting AI at global scale. And of course, this is the world we live in. This is a quick, coming back to reality. Today, the world is the internet, built decades ago, was entirely built on institutional trust. It was designed by people, for people, explicitly architected with people putting stuff together, and then only just decades later, trying to build security on the side of the whole mess, of the whole situation. So from the DNS and the certificates down all the way to domain administration, you have humans everywhere. None of this is verifiable. All of it is based on institutional trust. And then we end up in a situation where we have these web links or these any identifiers that are all local in nature, that are domain anchored in domains. And of course, the minute you anchor something in domain, you inherit all the privileged insiders, the institutional trust that you just can't verify. So that's the fundamental problem. So what I'm going to tell you about today is not another way or a better way of trying to fix this mess. What I'm going to tell you about is how do we remove all of this? how we remove all the trust dependencies that we have just taken for granted, that we assume cannot be removed, that we assume are just there and we have to live with it. So the idea is to remove all this, have a cryptographic infrastructure that is all the way down at the chip level, hence confidential computing, and how can we then automate things, cryptographic key exchanges across the internet. So of course we need to think different to do this, but more interestingly, we need to think first principles. And this is the summary of what we're trying to achieve. We have two entities. It's the Alice and Bob problem, right? For whoever's in cryptography, we have two entities. They're trying to exchange information, secure information sharing in a pairwise way. Pairwise means that there is nothing else in the middle. Of course, it's impossible, right? This is a goal. It's not possible. There will be systems here in the middle. But the whole goal is to remove as many trust dependencies as we can and get to the smallest attack surface technically possible. So what does this tell us? If this is what we want to achieve, we can already draw some lessons from that very simple diagram. The first one is that identity for any one of these entities cannot be assigned, cannot be administered. We cannot tell you, nobody can tell you who you are. It needs to be generated from within. In fact, it needs to be randomly generated from within. We'll see, we'll get to a cryptographic identifier in a minute. And it also needs to be automated because you don't want any human, any institutional trust to be there being able to take identities or reset identities. It needs to exist independently of every other entities. Every entity needs to have its own random identity that is completely independent of the existence of any other authorities external to it. The second lesson is that if there is nothing else, if there's only Alice and Bob, if there's only two entities, that means that each entity must be able to secure its own information without relying on any external source of trust, any other institutional trust. That's going to mean that every entity needs to have its own keys, essentially, its own encryption keys to be able to secure its own information. And the third lesson is that if we don't want anything in the middle, these two entities need to somehow find a way to establish a secure relationship in an automated way. And once they've established that relationship, then they need to be able to talk to one another, again, without any external dependency. They need to have direct programmable trust and say, I want to be able to talk to that guy. And once they know that that guy is part of the friendlies, then they can do a key exchange, fully automated, and then talk to them directly. If we can solve it for two entities, now we have the pattern, we have the building block that will enable us to build an entire system and to scale it at internet scale. Because the minute you can do with two, now you can repeat the pattern and you can create a chain. You can have entity A talking to B and talking to C, which is critical for chains of authority and delegation of authority in a way that is accountable when you know that who passed what keys to what other, for instance, to be able to decrypt something. But also chains of custody explicitly to say, hey, this information can mathematically only be accessed by these specific entities and nobody else, because nobody else has the key, because only those entities have the keys. And then, of course, chains of command, communication, controls, which are military terms. Kill chains is another term that they use, right? Making sure that you have accountability when somebody presses a button and prosecute a target. This is the military language. You need to know exactly who did what when and have cryptographic verifiability of this thing. And if we can do these chains, then we can start meshing things together. And you see here kind of a hierarchical pattern that emerges, right? Entity B, because it has relationship with A and C, can act as an introducer, can introduce A and C, and they can now talk to one another directly. This creates a pattern that can be repeated over and over and over again, and you can start imagining how you can start building a hierarchical recursive architecture. So now we need a new primitive that will enable the establishment of trust between two entities in a way that each entity is able to secure its own information without relying on anything external. The goal is to move away from institutional trust towards programmable trust, something that is inherently verifiable, digitally and programmatically by code. And of course, this is where I'm saying, and I keep, I'm a member of the CCC, I keep telling the CCC, agentic identity is the killer app for confidential computing, because if you want to move away from institutional trust, you must use a compute infrastructure that can be measured, that can be verified by software, so that you no longer have to trust humans or people or institutions to the largest extent possible. By the way, I'm making these bold claims. I'm not naive. There's no absolute security. I'm just trying to take shortcuts here to just paint a picture, right? And I'm talking really about a blueprint. We are very clear that our implementation may have bugs, may not be perfect. I'm talking about the blueprint here that gets us to a place where we couldn't go before. And then the next thing is that that's not enough, because as we said, you cannot have identities that are anchored inside domains, because that's an indirect reliance on the authority of the domain insiders, the people who have set up that thing. So what you need to move to is cryptographic identifiers that I hinted at before. Every entity in this system is represented by an identifier that is, in fact, both an identifier and a key at the same time. These are 256-bit or larger true random identifiers. What's interesting by just going to these kinds of cryptographic identifiers, now the identifier itself can participate in a cryptographic operation. That is what's going to enable us then to create the next primitive, which is what we call cryptographic linking. Cryptographic linking, I'm not going to go into the math here, but it's a very, very simple concept of you have an identifier that represents the entity. It is both its what we call a stem ID and its root key. You derive keys from it, and then you encrypt either other keys with it, or you encrypt information with keys that have been derived from the identifier. What that primitive gives you is it unites identity, information security, and compute. Because only the software agent that has access to that identifier can derive keys, can encrypt things. It collapses those things that normally were managed separately, right? You had identities and identifiers in identity systems on one side, and then you have key management in HSM and other place in another side, and then there's institutional trust to say this key belongs to that guy. By having cryptographic identifiers, because they're one and the same, the identifier and the key are one and the same, there is no dependency on anything saying this entity has these keys. They are mathematically united with one another. And now if you deploy software in a confidential computing environment using that construct and enabling cryptographic linking, you end up with properties that you just cannot do any other way. And happy to discuss this and take that offline, but essentially, because each and every one of these agents generate its own random cryptographic identifiers, it has its own global identity, it's going to be able to generate its own encryption keys, it's going to be able to encrypt its entire own lifetime memory, it's going to be able to hold cryptographic credentials to authenticate to other agents, it's going to be able to participate in transactions, send authenticated messages to others, confidential messages. And all of it is going to be running on verified execution, and will isolate both execution and information for each and every one of these agents. All of this, of course, has to be contained in a hardware-backed trust boundary that the TEs basically provide us. And this is what, of course, got the NATO guys quite interested. If you think about the traditional model, as we said, after the fact security, when you just put data in systems and then you try to apply security after the fact, you have all these trust dependencies on all the people that manage the security. You have a huge attack surface. If you think about all the trust dependencies that you have in any supply chain, even when everybody is signing everything with their own keys, now you have to trust all the signing infrastructure, all the people who manage the keys, all the HSMs that need to be involved. All of that stuff is trust dependencies to be able to verify information. With cryptographic linking, it's the reverse. We start from a place of secure place, the secure compute. We generate cryptographic artifacts inside that environment, and then we cryptographically chain everything else. there is no, there is some attack surface, but all of the external or the traditional system management just doesn't exist. We automate everything with code inside those agents. So how do we get to a system now that it can scale at internet scale? As we said, each entity needs to authenticate not to a conventional server that would be managed in the domain. They need to authenticate to one of these agents. They enroll, identify themselves, and authenticate to their own individual agents. And that agent will manage authentication, authorization, and key management on behalf of that individual entity. So now, and by agent here, I'm talking about software agents, right? These are not AI agents. We can plug models into it, so they can have small models, big models attached to it. What I'm talking about here is the deterministic verified code that establishes the identity and manages all the keys on behalf of that specific entity. So every entity has its own agent. Because we can deploy whatever code in those agents, we can match any protocol, any authentication methods. We can generate new agents to support any type of entity. Now, the question is, if every company, every entity here is doing this individually, how do we still connect those things, enable those things to find each other and talk to one another? And that's the next lesson of this exercise with NATO. It's following the path of least trust and smallest attack surface every step of the way, making sure that every time we try to add something to the infrastructure to enable that connection, that we maintain the smallest attack surface and the least trust possible. And when you do that, you end up realizing that you just need to, create a verification network, an attestation verification infrastructure, because you have to have, right? You cannot not have verification of your attested agents per the confidential computing paradigm. And then what you do is we create agents that verify other agents, and you start recursing this hierarchically so that you can grow the network without increasing its software attack surface. It's the same code that's going to repeat over and over again. You have verifiers that verify agents, and then you introduce shared verifiers that verify the verifiers. And you see this pattern here is again recursive. You could repeat it horizontally, vertically to create and scale to virtually any size. And once you have this pattern here, you see now that you actually have a path that is verified, that is all running in confidential compute, that doesn't rely on any external trust, that only exchange keys within secure and verified environments. Now the two agents can talk to one another. And if you repeat that over and over again, and you look at the general pattern that emerged, you end up with an infrastructure that doesn't have a single privileged insider, not even ourselves. When our CTO and when the system just came up, and for the first time, we saw the database filling up with encrypted information, encrypted with keys that only exist inside those environments, he came back, at stand-up meeting and say, it started working, but I have no idea what it's doing. It's completely opaque, even to us, which is, of course, as you can imagine, the kind of properties that NATO and governments are interested in. So, and then, of course, everybody told us, well, this is great, but, you cannot live in isolation. Come down to earth, Manu, you're just a dreamer. It has to function with the rest of the world. And of course, we need to be able to interoperate. So how do we do that? Well, the first thing we had to do is build agents that build other agents. So we built an agent, and our entire CI/CD pipeline, Rust code, we just push that in. It just automatically registers the fingerprints of new agents that are created into what we call the universal name system and the universal certificate authority, which is, I'm going to skip on this. I'm not going to go into details, but essentially the similar functions that you would have from the DNS and certificate authorities, but now at the individual agent level in a fully automated way running in confidential computing infrastructure. And then we have a deployment agent that then enables us to, again, fetch whatever it needs to verify an agent, and then can deploy that agent in a way that is, cryptographically chained to all other pre-existing infrastructure. So the mesh really deploys itself. without ever breaking that cryptographic chaining or cryptographic linking every step of the way. And then with that mechanism, what we started building is an identity conveyance system where we have human agents where Alice can authenticate herself to her own human agents through an app on her phone with with chaining, cryptographic chaining from the secure enclave of the phone to the agent over there. And then we build agents that can interface with the rest of the world. So for instance, we have OpenID Connect, SAML, SPIFFE, X509 certificates, whatever. So we can now interoperate and literally become a global identity provider between any type of entity on one side to any other type of entities on the other side, any legacy existing system, IoT device, or whatever. And the name of the game for us, of course, is to enable any organization to just add more their own agents to these things so that they can expand and grow the network. So if you zoom out and go back to the overall network and the DIANA thing, you end up with this kind of mesh network where every connection is pairwise, is cryptographically secure and anchored inside confidential computing environments. There is not a single human privileged access whatsoever across the entire network. Nobody, no human can see anything that's happening here. Again, bold claim, right? I know that there are some side channel attacks and other things, but in general, right, physical security is still necessary for confidential compute. But it is the state of the art in complete removing the institutional trust as much as possible. And then now you can imagine on the commercial side, what we want to do is be able to have every human having their own personal agent, every business having their own business and commercial agent, every nation being represented by a cryptographic agent within that system. And then, of course, every AI, which is the next use case, which essentially enabling every single company who wants to deploy their own AI agents to be able to anchor them inside that cryptographic infrastructure so that it can then build reputation for itself, have credentials to authenticate to other agents across domains, so that any company in any supply chain or consumer business, any seller agent to buyer agents can now find each other and transact in peace and in a fully secure manner. So 6 lessons. I think I'm over time. And then if you guys want to connect, this is my information on LinkedIn. The company is Hushmesh. And by the way, you guys should sign up and become members of the Confidential Computing Consortium. We need to make more noise about confidential computing, so please join. Thank you.